A cosmic enigma has finally been unraveled. The mysterious hyperspeed white dwarfs, hurtling through the Milky Way, may just have a clear explanation. These dense, cooling remnants of dead stars, like our sun's final stage, are usually slow-moving, quiet relics of the universe. But a rare few are anything but, zooming through space at breakneck speeds of up to 1,240 miles per second, 2,000 kilometers per second. That's fast enough to travel from New York to Los Angeles in under 2 seconds, and fast enough to escape the galaxy entirely. But here's where it gets controversial. Scientists have puzzled over these galactic cannonballs since 2018. Their extreme velocities suggest they were launched by violent cosmic events. But no single theory could explain both their blistering speeds and their unusually inflated, overheated appearances. Now, a groundbreaking study led by Hila Glanz of the Technion Israel Institute of Technology may have the answer. Using advanced computer simulations, Glanz's team modeled a scenario where two hybrid white dwarfs, a type with carbon-oxygen cores wrapped in helium shells, merge in a tight binary system. In the simulation, the lighter star is pulled inward and shredded by its heavier partner. As they interact, friction and compression heat the surface of the larger star, eventually igniting its helium shell in a violent explosion. This first blast sends a shock wave through the star's outer layers, which then compresses and heats the core, triggering a second detonation in the carbon-oxygen core. This chain reaction culminates in a thermonuclear supernova, leaving nothing behind except a flung, partially disrupted companion star. The study, published in Nature Astronomy, shows that this process naturally produces both the extreme ejection speeds observed by the Gaia spacecraft and the inflated, luminous profiles seen in real hypervelocity white dwarfs. Importantly, the explosion is relatively faint, so its debris disperses quickly, leaving little trace of a supernova. This matches observations of these stellar cannonballs flying through space without visible remnants nearby. The prevailing theory, called the D6 scenario, suggested that a massive white dwarf explodes after minimal mass transfer, leaving its companion intact. But this model struggles to explain both the extreme velocities and the puffed-up appearances of hypervelocity white dwarfs. Glanz's merger model, by contrast, shows that even a low-mass primary can produce a fast-moving remnant due to partial disruption. And because the resulting supernova is faint, its remnants fade quickly, leaving the ejected white dwarf looking like a lone wanderer. This discovery also sheds light on Type 1a supernovae, the bright explosions that act as standard candles for measuring cosmic distances and forging elements essential for life. Rather than pointing to a single origin, the study suggests these hypervelocity white dwarfs may arise from a diverse zoo of stellar interactions, including faint supernovae triggered by double detonations in mergers, like the one simulated by Glanz's team. Still, Glanz emphasizes that this is only part of the story. Future sky surveys, like those planned for the Vera C. Rubin Observatory, could help test these theories. If astronomers catch such a merger and explosion in real time, it could confirm the violent process that sends these stellar cannonballs flying across the galaxy. "It's not like we solved everything," she said. "We need to collect more pieces of the puzzle and continue exploring this zoo." What do you think? Could this be the definitive answer to the mystery of galactic cannonballs, or are there still pieces of the puzzle left to find? Share your thoughts in the comments below.